Hello students, welcome back to the second chapter of Mass Spectrometry, MS. Today we will study fragmentation patterns in MS. Fragmentation patterns in mass spectrometry refer to the specific icons produced when a molecule breaks apart during ionization. These fragments, which are smaller charged species, provide crucial information about the molecular structure of the compound. Each compound has a unique fragmentation pattern, which serves as a fingerprint for identifying and characterizing molecules. By analyzing these patterns, scientists can determine the structure, functional groups, and possible chemical reactions of a compound. Fragmentation patterns are particularly useful in elucidating complex molecular structures and confirming the identity of unknown compounds in various fields like chemistry, biochemistry, and forensic science. Alkanes often fragment by losing simple alkyl groups. For example, they can lose methyl, ethyl, propyl, or butyl groups, resulting in specific ion peaks. Branched alkanes tend to form the most stable carbocations during fragmentation. The mass spectrum of 2-methylpentane shows distinct peaks corresponding to the loss of various alkyl groups. These peaks help identify the structure of the compound. Alkenes typically fragment by forming resonance-stabilized allylic carbocations. This process results in specific ion peaks that can be used to identify the presence of alkenes in a sample. Aromatics fragment at the benzylic carbon, forming a resonance-stabilized benzylic carbocation. This carbocation can rearrange to form the tropylium ion, which is a common fragment in mass spectrometry of aromatic compounds. Aromatic compounds may also show a peak at M/Z equals 77, which corresponds to the benzene ring. This peak is a key indicator of aromatic structures in mass spectrometry. Alcohols fragment easily, often resulting in a very small or missing parent ion peak. They may lose a hydroxyl radical or water, and commonly lose an alkyl group attached to the carbonyl carbon, forming an oxonium ion. Primary alcohols usually show a prominent peak at M/Z equals 31, corresponding to H2C equals O+. Alcohols can fragment by two main pathways, alpha cleavage and dehydration. Alpha cleavage results in the loss of an alkyl group, while dehydration results in the loss of water, forming a double bond. The mass spectrum of 1-propanol shows distinct peaks corresponding to the loss of water and other fragments. These peaks help identify the structure of the alcohol. Amines often show an odd molecular ion peak, assuming an odd number of nitrogens are present. Alpha cleavage dominates, forming an iminium ion, which is a key fragment in the mass spectrometry of amines. Aliphatic amines undergo characteristic alpha cleavage, resulting in the formation of specific ion peaks. This cleavage helps identify the structure of the amine. The mass spectrum of an amine shows distinct peaks corresponding to the loss of various fragments. These peaks help identify the structure of the amine. Ethers fragment by alpha cleavage, forming an oxonium ion. They can also lose an alkyl group, forming either an oxonium ion or a carbocation. These fragmentation patterns help identify the structure of ethers. The mass spectrum of diethyl ether shows distinct peaks corresponding to the loss of various fragments. These peaks help identify the structure of the ether. Cleavage of bonds next to the carbonyl group is a characteristic fragmentation of aldehydes and ketones. A common fragment is carbon monoxide, but it is uncharged and does not produce a peak. The position of the carbonyl group influences the fragmentation pattern, producing specific ion peaks. Ketones and aldehydes undergo alpha cleavage of the bond between the carbonyl group and the neighboring carbon. This cleavage results in specific ion peaks that help identify the structure of the compound. The position of the carbonyl group influences the fragmentation pattern of aldehydes and ketones. The molecular ion of a specific compound has an M/Z value of 100, which helps identify the compound. Breaking the bond between the methyl group and the carbonyl group in aldehydes and ketones produces specific ion peaks at M by Z values 15 and 85. These peaks help identify the structure of the compound. Breaking the bond between the butyl group and the carbonyl group in aldehydes and ketones produces specific ion peaks at M by Z values 43 and 57. These peaks help identify the structure of the compound. Ketones and aldehydes with CH3 atoms away from the carbonyl group undergo McLafferty rearrangement. This rearrangement produces specific ion peaks that help identify the structure of the compound. Aldehydes, represented by the formula RCHO, can fragment to form an acylium ion. Common fragments include the molecular ion -1 and the molecular ion -29 for R groups. In the mass spectrum for hydroquinamaldehyde, we observe significant peaks at M by Z 91, 105, and 133, with the molecular ion peak at 134. Ketones, with the general formula RCR, fragment to form acylium icons. This can occur through the loss of R or R groups. The mass spectrum for 2-pentanon shows peaks corresponding to the loss of methyl and ethyl groups, with the molecular ion peak at 86. Esters, represented by the formula RCO2R, have common fragmentation patterns including the loss of OR and R groups, resulting in distinct peaks. In the mass spectrum for an ester, significant peaks are observed at M by Z 77 and 105, with the molecular ion peak at 136. With this, we've reached the end of Chapter 2 on MS. I look forward to seeing you in MS Chapter 3, where we'll continue our studies. Take care, and goodbye.